Hi all, welcome back to the second video of the week one. We are going to discuss the algorithms and computations of the present values and the discount factor that we discussed in the last video. So, Vikram, how do we proceed?
So I think if this was a standard intro financial economics course, where we would have gone on is to kind of like discuss how is this R determined and so on. But somehow we need to now figure out, because this is a computational finance course, we need to figure out how to translate this into something that the computer can help us with, right? So what are the things that you think that we should need to know, right? I see these words, algorithms, pseudocode. So how are they going to be helpful for us to think about the problem that we are tackling?
Yeah, great question. I think, what we need to do, what we realize from the last discussion is the last video that uh, computing the present value of future cash flow is very important. For example, in the slide, we can see P is the present value, and this is cash flow of tth time, and this is the discount factor of the cash flow. So, and then there is a sum. Now, if there is a long cash flow that are coming up, we need to do these all calculations and calculate the present value correctly. So what we need, we cannot do it like if there are like 50 or 60 or 100 cash flows are coming up, we cannot really do it in hand or using calculator. That's a little bit cumbersome and we will most likely end up making a lot of error. So what we can do, we can figure out some kind of algorithms. We write algorithms and ask computer to do this calculation for us. And we will just provide the cash flow and the discount rate. And computer will calculate this value, the present value of the all cash flow and give it to us. That will make our life very, very simple. So that is where the computations of and the concept of algorithms and pseudocode comes in, which will help us to compute these kind of financial values in to make our life simple and so that we can focus on analysis of the financial terms in long run.
So,
Is it
so
a
I think I understand this, but I'm just curious. Do you think that these words, algorithm I understand is a recipe, right? That
correct?
you should be precise in telling the computer. But these days, we can just use AI to, describe in English, this is the money that I'm going to receive and I'm going to get tell me what price I should pay, right? So why do we need to know these concepts of algorithms and pseudocodes anymore? Or do you think it's relevant at all? I mean, this is moving aside maybe from the goal, but I mean, I'm just curious as a
Ab-
person who is not, doing coding from the right from the beginning.
Absolutely great question. I think you are right, and this is I also think about it. But I feel like language, these large language models, so-called the Chat GPT, Gemini, Claude, they can do all these calculations in a split of a second. But at the same time, we do know they oftentimes they do hallucinate, and they oftentimes they give you a wrong answer or they make some assumptions without asking us the user, and that can end up you to value which is not you are looking for, and it can give you wrong answer. Well, if you can argue that going forward they are becoming better and better, fine, but end of the day there is a good possibility that these big AI models can make mistakes. Then we should at least figure out if it indeed make a mistake. We should be at a level where just looking at the value, we should be able to say that, what, looks like the LLM has made a mistake. It can't be this value. And we should be able to ask LLM or ask some Python to we should be able to codify by ourselves and write a code, run it in the Python and get the exact answer. So I think it is we all use calculator to add big numbers, but still we know that okay, we still being learn in the school how to add three digit number and get the correct answer. So it is a good skill to have. See, in the same spirit that we, even if calculator can add big two digit numbers, still we learn how to add big two digit numbers in the school, because it's a good skill to have. And I think writing an algorithm, correct algorithm, writing a pseudocode, writing a Python code is a good skill to have. It is not a redundant skill. It is a life skill one should have if
Right.
somebody
So
wants to
I
work in
think
Python.
I noticed that in the definition we have the word well defined, right? Which is carrying, I think, the most important load in this sentence about what is an algorithm, right? So the reason why we need to be well defined is this is the way in which we are communicating with the computer, and
Correct.
this is what the computer is going to rely in order to give an answer. So if we are being ambiguous, we possibly end up with getting something that we do not actually want, right?
Correct.
And forcing us to be well defined also forces us to understand, I think, the concept at a much better level. And I guess the reason why we are doing it in pseudocode is we want to be programming language agnostic. Is that correct?
Absolutely. So pseudocode, if you see, if my pseudocode is correct, then whether I'm running it in R or Python or any other language, it doesn't matter, right? So that is one of the reason. It is better to write it in the either algorithm or pseudocode, so that and also I think given that nowadays the LLMs are so good in writing codes, if you can give a very precise pseudocode, generally they're very good at writing the codes, Python code or R code, so that you don't have to worry about the syntactic error and all these things. That can be taken care of by the LLMs, but you should be absolutely correct when you writing a algorithm or a pseudocode.
So what does all of this mean for our pricing of bonds formulas? Can we look at it? What would the pseudocode for this be, for instance?
So pseudocode would be like, for example, it is a pseudocode, right? What we are saying to the, it is what we are saying to a computer that this is the name of the function. We are calling it bond price. And what we will do, we will provide in a vector, okay? We will provide the bunch of cash flows. Okay, if there are 10 cash flows, we will give them the cash flows and corresponding what time. Is it coming in the 6 month, 10 month, 12 months, or 18 months, whatever the time at which time point these cash flows are coming, and what is the discount rate that are we have to give.
So these are
Now,
our inputs, right?
these are our input to the function that we will write. Then we are starting with the what is the total. You can call it a present value. Actually, we have used it as a written as a total, but it is basically present value, because if you go back, this present value is coming as a total of these values. So that's why we are calling it as a total. But effectively, this is present. This total of these discounted cash flow is the present value. Okay, so we have initialized as a 0. Then for each cash flow and at each time point in this thing, then what you do first, you do calculate the discount factor, that is 1 over 1 plus r to the power t, right? So this is what, if you go back, yeah, this is 1 over 1 plus r to the power t. This is the discount factor that you compute. Oops, sorry. And once you get the discount factor, then you know the cash flow. What is the cash flow at that time? So if you multiply the cash flow at Tth time point by its corresponding discount factor, you will get the present value of that cash flow. And then you add that to your total plus that, and that will be your updated total. And you keep doing it for each thing. So this loop is for basically this sum. Okay. And then once you are done it, you return the value of the total. That is your present value. So this is the algorithm, or this is the pseudo code that you can think of. Um, so then what you can do, we can take this same spirit, we can write it in Python, we can write it in R, we can assign it to the student as a homework. What do you think?
Right, right. I think so. While you were discussing it, I thought of two things, right? One is if you go back one slide, uh,
Yeah,
it's intuitively what we would have done, right? So what did we do? We have cash flows at different period. We have the R, we have the time at which these cash flows come, right? So the first thing we basically calculated it is we have this cash flow. We need this element 1 plus R to the power T, right?
correct,
That's exactly first we calculated this 1 by 1 plus R to the power T. Then we calculated this CFT by 1 plus R to the power T. And then what we are doing is we are just adding this up, right?
correct,
And
correct, correct,
I think the other thing that we did is that we don't want to suppose somebody says, okay, this is for one instrument. We now have for another bond a different cash flow and different time period. We don't want to kind of like do the whole code thing again, right? We want to have one code that we can use for any cash flow and any time period and any discount rate, right? So that's I think the advantage of having a function with us so that we can actually do this over and over again without writing this whole set of codes over and over.
correct. Correct. Absolutely. Absolutely. That is another purpose. If you write it and then basically for any bonds, we can use this one set of function for any bonds. All you have to just provide the cash flows and the times and the discount rate, and it will give us the price of the bond back.
Right. So I think this has been super, at least for me, this has been useful in the kind of like thinking this is how intuitively I would do and this is how it is. But probably I'm guessing there are maybe other ways of also doing this. So that we will probably get to see later. Is that correct?
Yes, there are a lot of other ways. There are other ways. Mainly, issue will come whether when we have a different kind of discount rate at each different time point. So that will get another layer of complexity. So yeah, so that we will come at the later stage, maybe few videos later.
Okay.
So we can, yeah, some of the three observations at a bond when are pricing a bond. One is the sigma is the loop equivalence that I already told you, right? That this sigma, that sum in the math that we have done is basically the equivalent to this loop, right? That each step I'm just keep adding. So this sigma is the loop equivalence. Sometime it could be product. Depend if it is a product, then it would have been instead of plus, it would have been a star, right? Into like multiplication instead of summation. And then direct algorithm, the loop runs for a known fixed number of steps, one per cash flow. So basically for each T, I'm doing each T, I have a cash flow. For that cash flow, it is running. So this is another thing. Direct, everything is called direct. Such algorithms called direct algorithms. They finish in a predictable number of steps and produce an exact answer. There are algorithms which are not direct. They're called stochastic, sometimes called stochastic algorithm. You don't know at what step they will stop, and what the answer is not necessarily exact. So that is for a different kind of problems. And then scale invariance. So 10 cash flow or the 10,000 cash flow, the same loop handles the both. Algorithms don't get harder when the problem gets bigger. So this is where the interesting thing happens basically. So in the number of cash flow doesn't computer doesn't get scared. Oh, you have to do 50,000 additions. It just go ahead and do the additions. So that is a interesting part of the algorithm.
Probably the thing that changes is the running time. Although I think for this simple type of exercise, we won't understand the difference, but for more complicated
Correct.
kind of
Correct.
things that are there. So,
So
what are
here is,
you said that is the direct is the one way, right? Are there like things that we'll be seeing which are not direct?
yeah. So another is the iterative algorithm. So iterative algorithm are the one which makes the guess and then it refines the guess and then stop when it goes somewhere in the close proximity of the answer, it stops. Then question always arises that when do we stop? Where we will shall we always stop? How accurate the answers are, and these kind of iterative algorithms. One example is you compute value of e to the res x, which is a very important concept in finance. We will talk about it via Taylor series expansion. So this is like particularly, this e to the res x is a bit of a complex computation, and that can be very simply, simplified using Taylor series expansion. So shall we take a stop here and come back to the next video? What do you think?
I think that's a good idea, especially why is this e to the power x an important object in finance? I think that's what's coming up next, right?
Exactly, exactly, exactly. So see you in the next videos, students, and I hope you guys are enjoying this, lecture series. Let's see you in the next video.